So our next team is working on the same location, same problem, and they were tasked with evaluating the use of constructed wetlands for treatment. Constructed wetlands are probably the most common type treatment applied to this problem throughout this country. And they wanted to evaluate if it could, in fact, remove the mercury here. So, team Steady Solutions.
Okay, yeah, so like Dr. Urban said, we're Steady Solutions, and we're going to kind of talk about our constructed wetland design. Like I said, this is our name. It was created September of this year to kind of represent all of the work that we've put into this design. So to kind of introduce our team, my name's Maddie. This is Chloe, Cole, and Nicole. As you can see, we've got a good mix between civils and environmentals. No geospatials yet, though.
So to understand the problem, Pebble Creek is impacted with high levels of mercury. When it's in the form of micromercury, it can be a problem. It can cause bioaccumulation, and it can impact life in the stream. And our goal is to get this down to acceptable levels, which, as stated before, are 1.3 nanograms per liter. And as Dr. Urban said, we will be using wetlands to do this. So we broke this up into 6 sections. So we have preliminary research, subsurface flow design, size of the wetland, estimate schedule, challenges, and
So to kind of start off, we're going to discuss some of the preliminary research we did going into this project, specifically wetland types, flow regimes, and seasonal effects. So to start off, we kind of wanted to understand what constructed wetlands were. A lot of the research that we did resulted in wastewater treatment, which a lot of the constituents that you're treating there are a little bit different than the mercury we'd be treating here. There are a lot of different types of constructed wetlands, so we'll kind of jump into that a little bit later. But just a few advantages of constructed wetlands in general. They do tend to have lower operating and maintenance costs because once you build a constructed wetland, there's really not a whole lot more you have to do with it, especially with a gravity fed or a gravity flowing system like ours. If you do have pumps in there, then you might have a little bit more operating and maintenance costs. Wetlands can typically handle fluctuating water levels a little bit better than other systems. They're more aesthetically pleasing than bigger buildings. However, there are some disadvantages. So with constructed wetlands, there is a pretty high upfront cost. And later on down the road, depending on the wetland lifetime, you might have to replace a lot of that soil, which is essentially reconstructing the entire system. And then secondly, they do usually require more land just because the land is the main method of treatment.
So we needed to decide how our wetland was going to treat the mercury. And we decided to research 4 options, one being lime softening, precipitating the mercury, and then the last 2 were using adsorbents, such as iron oxide and organic matter. Ultimately, we decided to only investigate the iron oxide and organic matter because lime softening and precipitating mercury, either other teams were already looking into that, or we would have to add chemicals to get that to happen. And we wanted our system to be very hands-off once it was built. So then we just decided to investigate iron oxide and organic matter. So just to clarify, adsorption in our case would be the mercury binding to a surface, which would be the iron oxide or the soil. The iron oxide and the organic matter would be our substrate. And just to get a visual of what that might look like, the water will run through, the mercury will bind to, in this case, soil, and the clean water will just run through the system. So firstly, we needed to figure out for iron oxide what the pH would be for mercury to bind to the iron oxide. We used Visual Mintech for this, and Mintech is just a software where you can enter in your water parameters, and it will give you an output of water effluent constituents at equilibrium. Luckily for us, the pH coming from the mine drainage was 7.48, and the optimal pH falls within that range for mercury absorption for iron oxide. So we didn't have to worry about adding any acids or bases to kind of manipulate that process. Next, because mercury isn't the only thing in the water, we needed to investigate how other water constituents would react to the iron oxide. So we grabbed the 6 different constituents. We have magnesium, calcium, chloride, iron, carbonate, sulfate, and chlorine. So we plotted those concentrations against the absorption of mercury. And as you can see, for 4 of them, the more that you have, the less mercury absorption you're going to get. And so to us, this just means that the more constituents that are in the water, they're going to be coating the iron oxide, which makes it less efficient for mercury absorption. And so ultimately, we decided not to go with iron oxide. Next, we needed to see if organic matter was efficient. We had a lot of issues with Mintech, specifically with this part at the beginning of the semester, but ultimately this is what we came up with. We can get absorption of up to 100%. And we did this by manipulating the components of the soil. So there are 3 components: solid humic acid, solid fulvic acid, and dissolved fulvic acid. And by changing up those concentrations, that's how we were able to come up with these scenarios at the top here. We decided to go with scenario 5, even though that is the lowest concentration or lowest percentage that we see here. We did this because at this point in the project, we were already working with numbers from scenario 5, and we didn't realize that the other scenarios were a little bit higher. But because at 99.61%, we were meeting our treatment objective, and it's not that much different than 100%, we weren't really worried about it. So then we created a graph where we have the dissolved mercury on the bottom and compared to the solid phase of the mercury, which we then used to create a Freund-like isotherm graph. For the top graph, we went up to 1.3 nanograms per liter because that was our treatment objective. And at 1.3 nanograms per liter for our effluent concentration, the influent concentration would have to be 367 nanograms per liter, which is much higher than what has been tested previously.
Now, for different types of constructed wetlands, there's 3, anaerobic, aerobic, and compost. There's a little information on the slide about what each one does and what they're currently used for. To determine which one we wanted to use for our specific project, we decided to do a decision matrix that's split into 5 categories, graded from 1 to 3. As you can see in the middle, anaerobic is what we chose to decide for our constructed wetland. It's the score of 12.
So we also had to decide between subsurface and surface flow wetlands. So for surface flow, there are lower costs and they breathe that area, and they create a habitat for wildlife, and then they also prevent clogging, so they're better for systems with higher suspended solids. And then subsurface flows have higher contaminant removal per unit area, so although the other ones cost less per unit area, these can be smaller. And then they are more accessible for maintenance and have longer lifespans, and they're better for cold water conditions like the ones we experience. So ultimately, that's why we decided to go with the subsurface flow, because of the lower contaminant removal, higher contaminant removal, lower land area, and better for climate like the area. And then with that, we also had to choose between horizontal flow or vertical flow direction. And so we ended up choosing horizontal flow because there is lower operation costs and a longer life cycle, and then it also is in line with the analytic system.
Because the Keweenaw Peninsula experiences different types of weather throughout the year, this vary between month to month. We decided to look at the loading rate and the retention time with specific seasons. During the summer and winter months, due to precipitation and freezing temperatures, your loading rate and retention time are inversely proportional, which means that if you have an increase in loading rate, then you'll have a decrease in retention time, and inversely proportional. However, during the fall and spring, with the change of precipitation over historical land map, you'll have an increase of both. And we also looked into permitting with Eagle, and then also under constructed wetlands that fall underneath part 303 of National Resource Program.
So as engineers, we often spend a lot of time focusing on calculations and safety factors, but it's also important to mention the impacts that our projects will have. And so with this project specifically, first and foremost, and most importantly, we want to recognize the stakeholders that are involved in this project. So that's not only the community members surrounding the Osceola mine site, but also the fishermen downstream in fishing in Torch Lake. As Group 1 had mentioned, with mercury bioaccumulation, this is pretty hazardous, not only to the aquatic life, but also any fishermen who intend on eating the fish that they catch, but also anybody involved in the project itself. So that's owners, designers, construction workers, and anybody else. Additionally, there are some biking trails and railroads kind of going around the site that we're interested in. And so we just wanted to recognize that those are there and make sure that our project didn't impact them in any way. Thirdly, wetlands are actually really good for the environment because they do remove a lot of greenhouse gases. And then lastly, we did do a NEPA analysis, and we found that there's really not a whole lot of negative impact with introducing this wetland to the environment, but we did want to recognize the historical significance of the Osceola mine site. And so we were thinking about maybe including some historical signage, talking about the history of the site, or even an educational sign talking about how constructed wetlands work. So for our second part, we're going to kind of jump into the subsurface flow design, specifically how it works and the vegetation choice with it.
For the constructed wetland, we did a 3-layer system for each of the cells that we constructed. The layers would be of peat, 22 AA gravel, and clay. The reason behind we went to a 2-to-1 ratio of peat and gravel. This is due to the peat's medium porosity and low hydrological conductivity. So we introduced gravel into the system because of the higher hydrological conductivity. We can continue to keep the flow moving in our horizontal subsurface flow. Another reason behind this is if the mercury continues to be, if it stays and there's not enough permeability, then the vegetation, the mercury will just hold on to the peat, which in turn would be decomposing to the vegetation. We wanted to avoid this by increasing our hydrological conductivity.
So next we needed to decide what plants we would include in our wetlands. Plants are really important for wetlands because they can filter out the water and also remove metal contaminants. They can provide control for the sediment top layer of the wetland, as well as wind control and insulating for temperature. Ultimately, we decided to go with these 4 plants here because they're able to grow in high concentrations of organic matter. They're found in wetlands and or high soil or high wetness for the soil. And they're also native to the area. One thing we didn't want to do was to introduce invasive plants to the area and create bigger problems down the line. So that's why we wanted to go with native plants.
So now we're going to kind of jump into the system layout. So sizing, how we size the wetland, and then our need for a detention basin.
So this is the same isotherm graph from previously. We took the slope and the y-intercept, as well as other parameters, such as bed density, which was 40 grams per liter. Our empty bed contact time was around 93 minutes, which is just how long the contaminant will be, or the water will be in contact with the soil. And then the flow rate of 5.12 cubic feet per second. And we were able to get a total volume of 16,000 meters cubed. This will last us for up to 20 years. After 20 years, the soil will no longer be able to reduce the mercury down to our treatment goals, and so it will have to be removed at that point.
So kind of talking about the layout in general. So if you guys are looking at the screen, you can see the 8 little rectangles are the wetland cells. The top right is the detention basin. And then the blue line kind of coming in is the current stream. And then I'm gonna borrow this laser pointer because it's kind of hard to see. But if you look right here, there's like a little arcing section. We rerouted the mine drainage so that way during construction, we wouldn't have a stream flowing straight through where we are excavating. As Chloe had mentioned, the total area of the wetlands is about 16,000 meters cubed. We did decide to go with 8 wetland cells. This was based on 2 factors. One, land availability. We did initially try to do 4 wetland cells, but with the way, or with the plot of land that we're working with, it just didn't work out. And then secondly, a lot of design criteria about the required width of the wetland based on the hydraulic gradient. The detention basin is about 4,600 meters cubed, which I will get into the design of that a little bit later. And then also, like I mentioned, you can see the mine drainage rerouting and the existing stream. So talking about the individual cells of the wetland, we recognize that here in the US, a lot of things operate in feet and inches. And so we size the wetland based on that. And so each individual cell is about 95 feet by 48 feet. This is consistent with an aspect ratio of about 2 to 1. The vegetation layout you can kind of see here, a lot of those plants that Chloe had just mentioned, their scientific names are in the legend. We based this spacing off of not only the plant's spread, but the required spacing between plants. Thirdly, our inlet and outlet manifolds, we wanted to make sure that the entire wetland was being optimized for the treatment. So we introduced both an inlet and outlet that would spread through the whole system. And then lastly, we decided to go with a bed slope of about 1% to utilize a gravity fed system. So like I said, detention basin. So there's a difference between a detention basin and a retention basin. With detention basins, you expect there to be some dry periods, whereas with retention, you need to have a constant water level. So with this detention basin, we designed it for a 100-year storm event. We all heard of the Father's Day flood, so we wanted to be prepared in case anything happened. And in order to size this, we used the NRCS method. So we came up with an effective curve number based off of the land use and soil types. And then we used ArcGIS to kind of plot an effective drainage area. And we decided the total volume of the basin should be about 2.4% of that drainage area based off of research that we found. And additionally, a lot of the land use we found isn't developed. And so we weren't really concerned with introducing an overflow in the detention basin. So now we're going to kind of jump into our estimate and construction schedule.
Our total estimate is roughly a little over $500,000. Well, in this in turn, it's broken down into 3 categories: excavation, material layers, and other cost estimates. The other cost estimates, the pie chart shows every single line item split in percentage of the total overall cost. As you can see, the excavation cost, because it's such a big land usage, so far with the 16,000 meters cubed, and as well as our wetland cells, that was our biggest cost due to how fairly high it is. And then over the material layers are the 3 sum totals of each layer system overall, the total.
And then we projected this to take about 2 months to construct. We did have a little bit of overlap between the detention basin construction and the wetland cell construction. But we also kind of want to discuss some of the challenges we faced when designing this project.
So as I was saying earlier, we had a lot of issues with MinTech. There was kind of a big learning curve with it. And also we were misinterpreting some of the output results. So there are 3 phases of, or 3 solid phases of mercury. We were only accounting for the bottom 2 shown in the table. And so that's why we were only seeing a 27% absorption for mercury. At that point, we were trying to manipulate the LK2 and the log K value for solid humic acid to try to increase that percentage a little bit. And also we tried to change up the concentration for dissolved humic or fulvic acid in order to get that percentage to increase as well. And at that point, we were only able to get 29% absorption, which is still pretty low. But as you've seen previously, once we've added that top solid phase into our system, we were able to get nearly 100% removal.
So we also looked into pre and post filtration designs. We determined that additional filtration would be needed, and we looked into designs such as sedimentation basin and iron oxide reactive layer. We especially looked into iron oxide reactive layer and determined that this would not only not be useful because of methylation, and it also wouldn't be viable because there would be clogging and this would increase the amount of mercury that we absorb.
And then kind of talking about some of our future work, so conclusions and recommendations.
To conclude this presentation, our team can conclude that with our design horizontal panoramic subsurface flow, we can remove up to 99.6% mercury. It also is a viable, feasible option due to its low cost compared to treatment plants, and especially with a schedule of about 2 months.
So we created a streamlined life cycle assessment as well. And we just wanted to highlight 2 points. For the construction phase, that's where most of the energy is going to be used. And that's why in that section it's lower for our system matrix at the top. And then also for the system matrix, the soil cannot be recycled at all. So we'll just have to throw that out. And that's why that number is very low for the recycling and disposal portion. And then also for construction, the noise hazard is going to be a little bit lower, but only for the construction portion as well. And then the physical hazard will just be a little bit lower, just because mishaps can happen during construction.
And then just some recommendations that we'd like to leave anybody interested in this design with. Again, I mentioned the stakeholders because they are the most important with this design. Just making sure that you facilitate meetings and engagement with them. Additionally, we definitely want to obtain more flow rate data. As you guys saw, we used a flow rate of 5.12 cubic feet per second. And that's a pretty high flow rate given team one's conclusions. And so we'd like to have more historical flow or more flow rate data so we can kind of develop our design a little bit differently, specifically observing different monthly rainfall events and how the mine drainage flow changes based off of that. We also want to confirm and stake out any utility locations if there are some. Locate the groundwater table to ensure depth of elevations, although we don't think this is really a concern. Research more about how the plants are going to interact with each other. We did a lot of research with how the plants individually help the system, but we didn't really do much with, or there's not really much regarding how they interact with each other in a wetland. And then last but not least, educate the community on the use of constructed wetlands. This is a cool opportunity to kind of let people know what the system is all about. We'd like to thank the Civil, Environmental, and Geospatial Department for all of the support that you guys have provided to us over our years at Michigan Tech, and especially Dr. Urban for helping us a lot over this entire semester. So, do you have any questions for us? Yeah.
You have said it, but I might have missed, and I might have missed it, but I'm wondering if you have to, how you dispose of the wetland materials at the end of the wetland site. Is there a certain level of landfill that this has to go in, or what has to happen to that?
I think in our NEPA, I think Nicole can talk about that a little bit too, but it's not hazardous waste, so I think we would just have to throw it out regularly in a landfill. Is that right? Okay.
What would happen during summer? Would there be short circuiting in your wetlands?
Because we designed it for a 5.12 cubic feet per second, that was the max that's been historically recorded for this site. We figured, especially because their end flow rate was about 2 cubic feet per second, we're not really concerned with the wetland being short circuited with snow melt. Yep.
So did you do all the visual modeling at the pH?
Yes, we did it at 7.48. Yep.
Do you expect that change at all?
If it would change, I didn't expect that it would change. I think it was shown to be pretty consistent with the historical. I'd have to check on that. And then also we kept the temperature at 10 degrees Celsius for each run.
Yeah.
A couple of smaller ones, so
Yeah.
I may have missed this as well, but what is the wetland?
It's 20 years.
Okay. And then another question I have is about your Freundlich isotherm. It seemed like the intercept should be negative, but it was positive. Why is that?
I can go back to that.
Honestly, I'm not quite sure. That's just what Excel came up with. And I didn't even realize that until now, to be honest.
One other little practical thing. So in replacing the wetland, would it be feasible to replace one cell at a time? Or are you advise replacing everything all at once?
I guess we didn't really do much research into how the wetland would be replaced, but I would propose definitely replacing one cell at a time, especially because as you're moving through the wetland, the concentrations are going to decrease because the initial wetlands are going to absorb more, and then as they absorb more, the wetlands later in the system are going to have to kind of make up for that loss. So I think construction-wise, if this is a system that somebody wants to continue, not indefinitely, but for a longer time than that 20-span life cycle or 20-year life cycle, I would suggest removing the initial wetland cells first and then the following ones. We didn't necessarily design for that, but that wouldn't really be much of that would just be an additional piping system to make sure you'd be able to introduce the flow to the rest of the wetland cells while the first two are removed. Yeah.
Just a general question. What is the role of the plants in the wetland?
Well, at first, when I was researching the plants, I was trying to find plants that would remediate the metal, but we found that, okay, let me backtrack for a second. We were worried about mercury methylation, and so I was trying to find plants that would reduce sulfate and iron because of the sulfur and iron reducing bacteria that ultimately will methylate the mercury. So I was picking plants like the common like cattail and sphagnum as well. But the plants, they're really just for general purposes, like I was saying earlier, they can be used for aesthetics. They can help solidify that top layer of soil so that the water isn't peeling that away, and provide habitat for animals as well and create diversity. So just general things.
So they're not uptaking the mercury.
No, they're not meant to.
Well, thank you.